Good morning. I hope you can see the screen.
Yes, sir.
Right. So today we start a new topic. We are done with regular languages and finite automata. So to motivate context-free languages, just consider uh, the language of balanced parentheses. Okay. So for example, all these strings belong to the language. So all these belong to the language, whereas these strings do not. Right? And in your data structures course, you might have learned how to use a stack to recognize these kind of uh, strings. But now we are going to formalize uh, the study of languages, which include this particular language. So it is easy to show that this language is not regular. Here, of course, the alphabet consists of the two symbols, the left parenthesis and the right parenthesis. And this is important in parsing of arithmetic expressions and so on, programming languages, right? So this language is not regular, and you can use it using the pumping lemma. That's an easy exercise. So this is an example of a language which is not regular. It is, in fact, context free, right? And uh, so how do you define this language of balanced parentheses? Well, it's easy to give an inductive definition. You can say that epsilon is in the language. Um, and if x and y if both x and y belong to L, then uh, xy belongs to L as well as the expression containing open parentheses followed by x followed by right parenthesis also belongs to L, right? And nothing else belongs to L. That is understood when we define things inductively. Okay. So uh, this is the inductive definition of strings belonging to the language, right? And you may have seen the following way of defining it. So let E be the set of um, I want to say expressions, correct expressions. That is, strings of balanced parentheses. Then another way of writing this inductive definition is to say these three clauses, right? The first one says that the empty string is a valid expression. The second one says that a correct expression followed by a correct expression is a correct expression. And similarly, the third one says if E is a correct expression, then open parenthesis followed by E followed by close parenthesis is a correct expression. Okay, so this is what is known as a context-free grammar. Okay, and we say that the grammar, this particular grammar, generates the language of balanced parentheses. So we are coming to the definition now. And from now on, we'll use the abbreviation CFG, right? So what is this context-free grammar? It's a tuple. It's a four tuple, V, T, S, capital S, and capital P, right? Where V is a finite set of variables, and these are also called non-terminals. Or syntactic categories. So if you're talking about natural languages, the syntactic categories are things like noun phrase, noun, verb, adjective, adverb, and so on, right? So those are known as variables in our terminology. And T is a finite set of symbols called terminals. So the strings in the language are formed from these set of symbols. So the languages we are interested in are strings of terminals. Okay? And capital S is an element of V, and this is called the start symbol. So it is the variable that represents the language being defined. We'll see the definitions pretty soon. And P is a finite set of productions or rules where each production is of this form: A, right arrow, alpha. Okay. Where A is a variable and alpha is a string belonging to V union, this is V union T. So alpha is a string of terminals and variables, or terminals and non-terminals. Whereas, so on the left-hand side, you have a variable, and on the right-hand side of the arrow, you have a string, which may contain variables and terminals. Okay, so here's an example, the example that we just saw. The grammar for balanced parentheses. So here the start, the only variable is E, right? And the set of terminals is just the left parenthesis and the right parenthesis. And the start symbol is E. And there are three productions. The first production is E goes to epsilon. The second one is E goes to EE. And the third production is E goes to open parent E, close parent. Right. So this is the set of productions, P. And then we just, right? So this is V, this is T. Sorry, this is S, the start symbol. Right? So let us see a few more examples. Think of the language of palindromes. Okay. So a string W is a palindrome if W is the same as W reversed, right? So what is the grammar for palindrome? And let us say we are interested only in the alphabet containing 0 and 1. So the grammar will have a set of variables, and in this case, we need just one variable, S, the start symbol. And the set of terminals is, of course, the binary alphabet. And the start symbol is S. And the set of productions is as follows. Just think of the inductive definition of palindromes, okay? So the base clauses are, if you have the empty string, that is a palindrome, right? But also, if you have just a single symbol, that is also a palindrome, whether it's 0 or 1 or anything else. Those are palindromes. So these are the base clauses. And then the inductive clauses are, if you have a palindrome S, then adding a 0 at the front and end will give you another palindrome. And similarly, you can put a 1. If you already have a palindrome, you can put a 1 at the beginning and the end, and you have a palindrome, okay? And you don't need any more rules. These rules are complete, right? Now, for brevity, instead of writing so many lines, we often write it as follows in a single line, okay? S, right arrow, epsilon, then a vertical bar, 0, vertical bar, 1, vertical bar, 0 S0, vertical bar, 1 S1. So that is a compact way of writing the same set of productions, right? So these bars are separators, okay? And instead of using so many arrows, you just use one arrow. So henceforth, we'll be using this kind of notation, okay? So in both the examples we saw, we had just one non-terminal, but this is not always the case, or one variable, which was the start symbol. I mean, there has to be a start symbol. The set of variables is non-empty. There has to be a start symbol, right? Okay, then, yeah. So let's take another example. And this is something you'd be familiar with, maybe from your data structures course. Consider the language of arithmetic expressions. And we'll use the variable if to denote those, built out of or built from integers and we'll just use n for this, n for number, and identifiers. And we'll use the variable I for identifiers using only addition and multiplication. So no subtraction, no exponentiation, division, etc. Right? So very simple, right? So what is the grammar? The grammar, the context-free grammar, this will have three variables, E, I, and N. And let us say that this, to simplify things, that these are the terminal symbols. A, so these are from the alphabet, right? These are letters, small case letters. And let's say that we have just two small case letters, A and B, and no uppercase letters. And also, instead of 10 digits, we just have 0 and 1, right? Just to simplify, this is just an illustration. And you also have open and closed parentheses. And you have the operations plus and star. Well, let us throw in minus as well. So include the addition, subtraction, and multiplication, right? And the start symbol is E, and P is the set of productions, which will be written below. So this is the set of variables. This is the set of terminals. This is the start symbol. And these are the productions. So in this case, the productions are as follows. E can generate an identifier. An identifier by itself is an expression. So is a number, right? Or you can have the sum of two expressions. Or you can have the product of two expressions. Or you can simply have uh, an expression enclosed in parentheses. But we don't seem to have a minus here, which means that this is a unary thing. This minus is a unary minus, right? And it'll show up when we define the numbers, right? And an identifier can be a single letter, so either A or B, or a string of non-empty string of letters. Okay, so we don't even allow digits and special characters. Just to simplify things. And by the way, this identifier can be specified using a regular language, right? As you can because it's just a string of any string of lowercase letters, non-empty, of course. Okay. So that's a regular language. Even if you allow uppercase letters and the lowercase letters and special symbols such as underscore, hyphen, etc., dash, and you impose the restriction that it must begin with a letter, either lower or uppercase. Even in that case, it's a regular expression. It's a regular language. Okay. And whereas the language of expressions is not a regular language. And let's say that the numbers are just non-empty strings of zeros and ones. And you can also have unary minus and unary plus. Okay. So this is the grammar. Of course, this grammar is a bit strange because you can get weird expressions like plus a plus 2, right? Can you see that this particular string is in the language? Because, you know, this is a unary plus 2, right? So similarly, sorry, this plus a will not be there. That unary sum applies only to numbers, not to identifiers, right? So this is an identifier. And plus 2 belongs to n, right? And any identifier is also an expression, and n is also an expression. So ultimately you get e plus e, right? Which is an expression. Yeah. Enough examples for now. Let me just briefly mention the applications. Okay, the main application or the original application in computer science was parsing of programs, right? This is a phase in compilation of programs. Not just compilers, but compilers, interpreters, and in any application which requires handling of user provided input strings, they need to be parsed first before any kind of processing. Okay. So compilers are just an example. Most front-end modules will do some kind of parsing. Okay. So if you have done shell programming, those are like interpreters. So they also do parsing. Okay? So that's an important application. And then in markup languages like HTML and XML, these documents have a tree-like structure. Okay, so they can be specified by context-free grammars. Finally, model of software. Why is it important here? Because recall that in a program, you will have functions or what are called functions or procedures or subroutines. And these call each other. And the pattern of calling and returning uh, is uh, is something like the language of closed parentheses, except you have different kind of parentheses for different functions. Okay, so context-free languages play an important role there when you have to talk about, you know, the order in which functions are called, for instance. Okay. Actually, the context-free languages were introduced by Noam Chomsky, the linguist, um, for describing the syntax of natural languages, such as English. Right? But they were found to be convenient for describing the syntax of programming languages as well, and hence their adaptation in computer science. Okay, so that was the original motivation. Okay, so we have defined a grammar. The next thing to do is to define how a grammar defines a language. So that leads us to the notion of derivations. Right? Just to take an example, if we want to talk about for a given grammar G, let's take the language of expressions, right? So we want to ask, sorry, what are the strings in the language of arithmetic expressions as defined above? As defined by the grammar here, right? The language of arithmetic expressions. So how do we find those strings? Well, we start with a start symbol, which is E in this case. And we say that in one step, E derives, and we use this double arrow for this. Remember, in the productions, we use single arrows, but the relation of derivation is depicted by a double arrow. We say that E derives the expression E derives the string E star E, right, in one step. And this itself, by rewriting the right E, by using an appropriate production, okay, we can go on rewriting like this. Let me write on separate lines, okay? So here, we using the production so each derivation is actually a sequence of rewrites like this. So this can be rewritten to E star n. And here we use the production right? It is this E which is being rewritten. And this will derive in one step E star minus n. And here we use the production. So this is being written, right? This one here, n goes to minus n. And so on. I could go on doing this, but let's just say I rewrite this E to an identifier. And I rewrite that identifier as A. And I rewrite the variable n as 1, say. Right? So that is an arithmetic expression. It looks strange, but if we use this grammar, then it is a valid expression. Okay, so a derivation is simply a sequence of steps where we start with the start symbol, and at each step we replace a variable by the right hand side of a production for the same variable, right? So here we replace this variable here, right? Okay, so here are the formal definitions. Let G be a grammar. CFG, context-free grammar. And let's fix that. So we say alpha A beta derives in one step. We'll use this symbol, and we'll often drop G from this subscript when the grammar is clear from the context. Alpha, gamma, beta, where A is, of course, a variable. And alpha, beta, and gamma are strings of variables and terminals. And these could be empty as well. And a right arrow gamma is a production of G. Okay. Any doubts about this definition? So this is often called single-step derivation. Right? So the string on the left-hand side must have at least one variable. Okay. And any variable in that string can be rewritten uh, by a string on the right-hand side of a production to give a new string, right? And that's what a single-step derivation is, right? And often we write, when G is understood, we write just the double arrow without the subscript. And further, this double arrow star denotes 0 or more derivation steps of this double arrow, right? So if you think of double arrow as a binary relation between strings, then this double arrow star is the reflexive transitive closure. That is the smallest reflexive and transitive relation containing double arrow, okay? Which is the same as saying 0 or more derivations of of G, I should say. Yeah. Right? So for instance, in this case, we say that from E, you can derive in 0 or more steps. Well, the star is actually written above the arrow. We can derive a star minus n, for instance. Okay. And of course, a symbol can always derive, a string of symbols can always derive that same string of symbols, because I'm including 0 here, 0 or more steps, or indeed by reflexivity. That's another way of saying it, right? So given this notion, uh, a language the language generated by the context-free grammar G, and this is denoted LG. This is simply the set of all strings which belong to the set of all strings over the terminal symbols. Okay, so no variables here, only the terminal symbols, such that starting from the start symbol, you can derive W in 0 or more steps, i.e., the set of all strings of terminals derivable from the start symbol. And finally, we say that a language L is context-free if there is a CFG G such that L equals LG. So that uh, let us go back to the example of palindromes. What is the grammar? So that is the grammar. And the claim is L of G is indeed the language of palindromes. How would you prove this?
Induction on length of string.
So we show well, we have to show two things. Okay. Uh, let's call this language PAL, right? Then we have to show two things. One, so we have to show that these two sets are equal, which means we have to show inclusions both ways. So we have to show the set of palindromes is contained in LG, and two, LG is contained in PAL. That's the only way to show set equality. Okay? Every element in the left set belongs to the right set, and every element in the right set belongs to the left set. So you have to show these two things. So please be careful. It's not enough to show only one way. So as you said, we show one by showing or proving by induction on the length of a string W that W belongs to PAL implies that we can derive W from S in 0 or more steps. Okay, so this is an easy proof. I leave that to you. And how do you prove 2? By induction on the number of derivation steps that if we derive W, then let me just use the implied symbol here. then it is a palindrome. Okay, so you got to show both these things. One is by induction on the length of W, and the other way is by induction on the number of derivation steps. Okay, so let's stop there.